Welcome to Massive Open Online course on fluid flow operations. So, in this lecture we will continue the hydrodynamic aspects of multi-phase flow. We have already discussed something regarding that hydrodynamics of two-phase flow and flow pattern, and also some characteristics of what is that transition of that flow pattern, and also the frictional resistance and how to actually analyze that frictional pressure drop, and also hold up characteristics, that is volume fraction of the phases in the two phase system. Now, in this lecture we will discuss something more about that what should be the phase interaction. That means, here if there is a two phase flow, if there is a flow of gas and liquid in a vessel, then there will be a formation of a bubble in a liquid medium. Then what should be the interaction of the bubble and bubble, how the bubbles will be coalescence and bubbles will be break up into a smaller or finer bubbles. And you know that also after breaking up the bubbles or coalescence, you will see the interfacial phenomena will change. In that case, after breaking the bubbles, you will get more interfacial area of the gas and liquid, and also what should be the mixing characteristics of the phases that you have to know, because this mixing characteristics of phases of course will affect the yield of the processes. And also interfacial phenomena, it of course one of the main important characteristic factor of multi-phase flow systems, because this interface, through the interfacial area there will be a mass transfer. When you are going to separate one phase from the another phase or mixture of phases, then you will see the mass transfer will be happened through the interface, and in that case what should the interfacial area that should be accounted. And during that phase interaction, how this interfacial area will be actually changing, that also to be known. So, we will discuss here very simple way what is that, how to actually calculate that interfacial area. Before having that interfacial area, what should be the size distribution of the particles, like if it is bubbles, then how the bubbles will be forming and how interfacial area will forming, and also how to obtain that size of that bubbles, that ultimately that size of the bubbles will give you the interfacial area. Now, what should be the distribution of the bubbles in a particular systems of gas and liquid. In that case, gas will be dispersed in the dispersed phase of bubbles, then all the bubbles will not be uniform in size, and also the number of bubbles will be changing. So, you have to know the distribution of the bubbles in the column, then you will be able to analyze in which range of bubble this particular process of the separation, or in chemical engineering, biochemical engineering processes are happening. So, those things to be known. Now, phase interaction means, here if you are considering gas liquid two phase flow, then there will be bubble coalescence, bubble breakup, bubble size distribution. Even if you are considering liquid flow systems, then what should be the liquid droplet coalescence, droplet breakup, and its size distribution. For gas liquid three phase flow systems, then bubble solid among liquid and liquid interactions. So, in this case we are having the interfaces between the phases as bubbles or droplets. You will see one examples like droplet, if kerosene is flowing through the pipe in a continuous water medium, then you will see that there will be formation of what kerosene droplet, that means which is dispersed phase. Generally the droplet will be forming for that lighter phases. Here kerosene is lighter than water, and in that case the kerosene droplet will be forming just by distribution of the energy on the liquid, and there will be change of that droplet size based on that interfacial phenomena, like is there any physical property change or not. Even also the inertia effect will be on the droplet surfaces. Then what should be the stable droplet or bubbles, that will be discussed here. Now, have a look on this diagram. What is this? Let us do an experiment of gas liquid operation. In this case, here if you observe that there is a flow of gas in a column, the gas is supplied from the bottom of this column as a dispersed phase of bubbles, and then gas is actually distributed through the distributor, and the distributor will have certain hole size, and through which this gas will be passing, and then gas will be dispersed in this continuous liquid medium here as a dispersed phase of bubbles. See here, bottom part, from the bottom part of this column, gas is supplied by a compressor, and from that compressor gas is coming through a rotameter. This rotameter will give you the measurement of gas flow rate, and after rotameter it will come through the what is that solenoid valve, and whenever it will be solenoid valve is being used for sudden stop of this operation, and it will come to that distributor, and through the distributor gas is distributing. And here also liquid is actually poured into the liquid by a pump from a storage tank, and it may be continuous, it may be batch wise. So, if you are considering that here batch wise, what will happen, then only some amount of liquid pool will be in the column, and in that liquid pool this gas will be dispersing as a dispersed phase of bubbles, and then gas is coming from the bottom of this column to the top, and then what happened, this gas is disengaging, and it will be collapsing at the top of the surface of this gas liquid mixer, and then it will be coming out to the atmosphere. Now, this is an example like this. If you are actually apply this process for carbon dioxide gas absorption from the atmosphere, then you have to supply the mixture of carbon dioxide gas and air that is from the atmosphere, and it will be passing through the distributor, and as it is dispersed phase of bubbles, that is carbon dioxide gas bubbles and air bubbles will be coming out, and those carbon dioxide gas bubbles will be actually flowing through this column, and during that flow, since carbon dioxide gas have some interfacial area between that bubble and liquid. So, through that interfacial area the carbon dioxide gas will be absorbed or transferred from this here from carbon dioxide gas bubbles to the what is that liquid medium. Here liquid may be here sodium hydroxide solution you can use, or some amine solution also you can use, where the solubility of the carbon dioxide is more compared to the water. That solution also you can use as a solvent. So, in that solvent you can absorb this carbon dioxide here. So, this is one example. Now, some hydrodynamic characteristics that you have to study for this. Now, we have already discussed what should be the hold up of this gas or carbon dioxide gas here. That is one of the important hydrodynamic characteristics, because hold up will give you the interfacial area, that is because specific interfacial area is related to this hold up of this gas, and more the hold up of the gas you can expect more interfacial area, more mass transfer and more absorption there. And other characteristics like what would be the frictional pressure drop, that already we have discussed, and how to estimate the frictional pressure drop, that you can measure by manometer or some other sophisticated instrument can be used to measure this pressure drop, and after getting that pressure drop at the particular that pressure drop you can apply this process here. Even sometimes if you increase the pressure drop or control the pressure drop, you can expect more finer size of bubble, and in that case you can expect more interfacial area and more mass transfer there. But sometimes higher pressure may decrease the mass transfer efficiency. In that case you have to optimize at which pressure drop, you have to actually perform this experiment or these processes. So, there will be an effect of pressure also for controlling this bubble size there, and also the flow rate of the gas is also one important variables by which you can get that size of the bubbles, whether it will be more finer or coarser, that depends on the inertial force or kinetic energy distribution in this column whenever flow will be there. So, in that case, based on that, maybe at higher flow rate, you will see there will be a more probability of coalescence of the bubbles and more breakage of the bubbles. In that case, which one will be more dominant factor, whether it should be coalescence or breakup, but simultaneously that coalescence and breakup will happen. In that case, maybe more finer bubbles may obtain or coarser bubbles also may obtain. That variables are that controlling of that variables at a particular condition that you have to actually analyze, and based on which your performance of the process will be calculated. Now, let us here consider that bubbles here, whatever size is formed during this operation. So, what you will see that how to actually analyze this bubble size there, because this is one of the important factor by which you can get the mass transfer efficiency. Now, that how to actually estimate this bubble size, very interesting, that what to do, that you have to use one camera that can be placed that is in front of the column, and background of the column you can make it black, so that you can get more contrast bubbles there. And if you are making this column as a rectangular column, then it will be more actually accurate for measuring this size of the bubbles. So, one method is very common method, that is photographic method. In this case, one high speed camera you have to use, and you have to capture the bubbles whenever it will be moving there. So, during that movement of the bubbles, if you capture the bubbles at a particular position like here shown, at this position if you capture the bubbles, and if you magnify that bubbles after actually refinement, then you will see this type of bubbles you can expect there, this window. So, these are the bubbles that you can get. So, before actually taking this that is snapshot of the bubbles, you have to make a, or you have to attach a scale on the what is that wall of the column, because that scale will be actually actual in size. What should be that? You have to calibrate that bubble size with respect to this scale, and you can calculate the actual size of the bubbles. Now, what to do? So, after capturing this bubble by this camera, you have to actually refine that snapshot by some suitable software, that is maybe images software, or maybe what is that Photoshop software. You have to refine that software, and contrast and even some color contrast to be matched in such a way that you can get the finer contrast bubble, and also the interfaces of the bubbles will be more actually visible. And in that case, after getting that actually refinement of this picture of these bubbles, you have to analyze the size of the bubbles. Now, what to do? You will see in this snapshot of this bubble, you will not get only single bubbles, there will be more than I think 500 bubbles, even more also, a number of bubbles you can expect there. So, in this case, how to actually measure that bubble size? So, what you have to do, you have to individually identify bubble in this picture, and what you have to do then marking out this what is that surface of the bubbles here. Let it be here one consideration, let it one bubbles here, this is your one bubbles. So in this case you mark it out this bubbles, and you just measure the perimeter of this bubbles. And how? So you have to use one software, image analyzing software like ImageJ Plus, even you can say Image Pro Plus software, even some other commercial software. There are several different types of softwares are available in the market, and so you can use that software, and by that software you can directly actually measure this perimeter of this bubble. Now this software may give this perimeter in terms of pixel or some other in terms of parameters. In that case, what you have to do, you have to first calibrate this size of these bubbles in this case. So you have to mark it out this to this length. This length is suppose 1 centimeter. So this centimeter will give you a certain pixel as per the software. Now this length will give you the pixel of suppose 1 centimeter is giving you equivalent to suppose thousands pixel. Now in this case then 1000 pixel is equivalent to 1 centimeter. This 1 centimeter is the actual length. Now if you are calculating the perimeter of this bubble, then what should be the pixel of these bubbles, that is pixel of the perimeter of this bubble. So pixel here in this case maybe it will be 500 pixel. So this 500 pixel is equal to 1 perimeter. That means here then what should be that in actual length, then 1000 pixel is 1 centimeter, then 500 pixel will be equals to 0.5 centimeter. So it will be 0.5 centimeter. So this is your actual length. Since it is a perimeter of this bubble, then what should be the diameter of the bubble? And in this case you may not get the spherical bubble. It may be different types of different shapes bubbles. It may be oblate, it may be spheroid, it may be some other ellipsoidal bubble. So in that case you have to consider that equivalent diameter of the bubble. What is that equivalent diameter of the bubble? In this case you have to actually equalize the equivalent volume of the bubbles which is coming here in this case. Let it be considered here, if we are considering this perimeter of that bubble here, this perimeter. So if we consider that one bubbles whose volume will be the same volume of this bubbles, then what will be the perimeter of that equivalent bubble? So for that, for the calculation of that perimeter, it will be pi of dE. dE is the equivalent diameter of the bubble. So this pi d will be equal to what? In this case this 0.5 centimeter. So dE will be equal to 0.5 by pi. So this is will be your bubble diameter as 0.5 by pi. So this will be your actual equivalent diameter of the bubble. So in this way you can calculate what would be the size of the bubbles. Now in this case you have to have 1000 bubble or more than 1000 bubbles to calculate, because all the bubbles will not be same in size. So in that case you have to calculate what will be the mean of that bubble. Generally for any physical operations or chemical engineering operations, this type of discrete interfaces, in that case outer mean bubble diameter, that is called volume to surface area ratio mean diameter is considered. So volume to surface area ratio mean diameter is defined as this as D32. It is denoted by D32. It is defined as summation of Ni dBi cube divided by Ni dBi square. Here dBi means ith bubble diameter, that will be equivalent for that individual bubble equivalent diameter, and based on this equivalent bubble diameter, if you consider suppose 200 bubbles, then individually for 200 bubbles you have to measure the perimeter and then equivalent diameter, and then getting the cube of that equivalent diameter and square of that equivalent bubble diameter. Then after substitution of this, you can get this dB32, that is a outer mean bubble diameter, or it is called volume to surface area mean diameter. So this will be your actually mean diameter. So out of maybe 1000s or 100 or maybe more than 100, or maybe that is as per you suitable, but it should not be less than 100 bubbles, then it will be some erroneous, but if you are considering more than 100 bubbles, then maybe error will be less. So after getting more than 100 bubbles and calculating the mean diameter of the bubbles by this formula, you can analyze what should be the number of bubbles here in this particular snapshot of this window, and in that case you can calculate that number flux of the bubbles. Number flux means here per unit time how many bubbles will be crossing that cross section at which you are taking this bubble. So in this case that number flux can be denoted by n dot z. The z is the particular height of that column. So at this column, this is your z. So at this height, if you are taking these bubbles and analyzing and getting the outer mean bubble diameter, once you know this outer mean bubble diameter, then you will be able to calculate how many number of bubbles actually formed in that particular or moving in that particular cross section. So it will be 24 into Qg by dB32, this is outer mean bubble diameter cube into dc square. What is that actually? This is nothing but that number of bubbles. First of all, you have to calculate what will be the volume of that gas here. That volume it will come, what will be the volumetric flow rate of the gas that you are supplying there. Now, since this window will be a mixture of gas and liquid, so in that case what should be the amount of particular gas there? If you know the gas hold up, already we have discussed how to calculate the gas hold up. If you know the gas hold up there, then what will be the amount of gas that is passing through this particular cross section? So that will be simple by Qg into that is hold up of that. So that is a fraction of that total mixture of gas and liquid here. That fraction depends on the gas hold up. So once you know that Qg volume or volumetric flow rate of the gas there, and if you divide it by the volume of the individual bubble, then you will be able to calculate what should be the number of bubbles in that particular cross section. So in this way you can calculate what will be the number of bubbles. Now you will see there may be 100 bubbles, more than 100 bubbles, even thousands bubbles, you do not know. But if you are considering suppose only 200 bubbles, let us consider only 200 bubbles. So individually you have to calculate what should be the size of that 200 bubbles. So you have to segregate all this bubble size into a different classes. Like if you are getting the bubble size range from 0.1 millimeter to 5 millimeter. So in that there is a wide range 0.1 to 5 millimeter range of this bubble size. So you just classify this bubble size range into a 10 classes, like here 0.1 to 0.5 one class, 0.5 to 0.7 that is one class, or equal distribution, equal length of classes you can consider. Just divide it by 0.1 to 0.1 to 5 millimeter, then that means here 0.3, 0.1 to 0.31, 0.3 to 0.6 another class, 0.3 to 9 another class. Like this you will get 10 classes. So, out of that 10 classes, what you have to do, that you have to count how many number of bubbles are coming within that particular class. So, in that particular classes, suppose 0.3 to 0.6 millimeter diameter range, we are getting only 5 bubbles. Similarly, 0.6 to 0.9, we are getting 10 bubbles. 0.9 to 1.2 millimeter, we are getting what is that, only 25 bubbles. Similarly, 1.2 to 1.5, in that class we are getting here 20 bubbles, and then 1.5 to 1.8 millimeter range, we are getting maybe only 6 bubbles. So, in this case you will see there will be a number of bubbles that will be depends on the classes, that within a certain classes how many bubbles, that depends on the size of the bubbles. So, if you are getting the that means you will see some within a particular, that is a very small region of bubble size, you will see there may be more number of bubbles, or maybe more number of bubbles in the higher range of, that is bubble sizes, that depends on that size of the bubbles. Now, if we represent this number of bubbles graphically, what we can say, that here let us do a graph here. In the x axis you just represent the size of the bubbles as dB, and accordingly here within a certain range of this dB you are getting this number of bubbles. In the y axis your number of bubbles, in number of bubbles, and here again another range bubbles you are getting this number of bubbles, and another range you are getting this number of bubbles, another range you are getting this number of bubbles, another range this number of bubbles. So, in this case if you add this number of bubbles here in this axis, we are getting this type of distribution. Here one example of this distribution from the experimental results, it is given here in this case like this. So, this is one distribution, how, see here, see this is a classified different in different classes, how number of bubbles are there, but here relative numbers here. So, number of bubbles, it will be represented as a frequency, that is number of bubbles within a certain range of bubble sizes, how many numbers of bubbles is coming, that are analyzing, that will be your frequency of the bubbles. And you can represent the size distribution based on this frequency, that is number of bubbles, or you can represent the density of the bubbles. What is that density? That means here per unit cross sectional area, or you can say per unit volume of that cross sections, that you are consider how many number of bubbles are coming there. So, if you divide that number of bubbles divided by that is volume of that particular cross sections, then you can have the density of the bubbles. So, you can represent the in terms of density of the bubbles then as a function of bubble diameter. Also, you can represent the size distribution based on what is that relative frequency. What is that relative frequency? You will see if you are considering the 200 number of bubbles, then for individual classes how many numbers of bubbles are you are getting. If you divide that number of bubbles by the total number of bubbles, then you will get the relative frequency, and accordingly as per the bubble class based on the size you can get the what is that relative frequency accordingly. Then you can represent it in a graph, then it will be called as size distribution of that bubble. And this bubbles formation of course depends on the what type of distributor you are using. If you are using more you know that finer hole based that is distributor, you can expect more finer bubbles there, but sometimes this size may depend on the physical properties of the system also, because If you are using more viscous liquid, in that case you may expect sometimes finer bubbles there. Even if you are using some surfactant, or if you reduce the surface tension of the solution, you will see you may get the more finer bubbles there. Size will be reduced if you add some surfactant there. And during that addition of the surfactant, you may expect the foam also, because foam is something different from the bubbles. That foam will have certain shape of that what is that hexagonal, some structure, but in the bubbles will not have some structure. In that case it will be having that what is that round shape. It may be a different shape, but it will not have the particular structure. So, foam, that is also air bubble. So, in that case it will have some particular regular structure. Foam also can be measured in that way, because that is also important for application of froth flotation process, and in that case for mineral beneficiation the froth flotation is important. So, in that case this bubble size or foam size analysis is also important. Another important point, that if you are using distributor in such way that that nozzle type distributor, in that case you may expect bigger bubbles, but sometimes due to the shear effect from the nozzles, there will small bubbles will form, but after certain time it may coalescence to each other based on the physical properties of the system and forming a bigger bubbles. Sometimes from the jet also you will see there formation of elongated bubbles. So, you will not get that spherical bubbles there. So, in that case you have to carefully analyze whether you should consider that Sauter-Mean bubble diameter or not. Generally for that it is not suggested to consider that Sauter-Mean bubble diameter. So, only that length and what is that cross section of the bubbles you have to consider. Like bullet shape bubbles, sometimes it is forming in slug flow system. So, in that case what will be the length of the bullet, what will be the cross section of the bullet, that way it will be analyzed, not like that mean diameter will be considered. So, based on that bullet volume and surface area, what should be the interfacial area for that mass transfer, that is generally being considered. But for other type of bubbles, that you have to consider in this way, what should be the Sauter-Mean bubble diameter there. Generally for discrete bubble it is considered, and generally bubble diameter up to 5 millimeter, this type of this Sauter-Mean bubble diameter is considered as a mean diameter and further analysis. And what about then liquid operation? This is suppose this gas liquid operation, what droplet formation in liquid operation. Suppose this kerosene is supplied in a pool of what is that water. So, from the bottom, then you will see the kerosene will be flowing in that water medium as a dispersed phase of droplet. So, in the same way, by camera you can take the snapshot of that droplet and then analyze what should be the size of that droplet, and also in the same way you can calculate Sauter-Mean bubble diameter and then what should be the interfacial area. Once you know that Sauter-Mean bubble diameter, then interfacial area, that means specific interfacial area, it is generally interfacial area or surface area divided by the whole volume of what is that gas liquid mixer or liquid mixer there. So, in that case for gas liquid operation, that specific interfacial area is denoted by A, and it will be 6 alpha g by Sauter-Mean bubble diameter D32. So, this is your formula to calculate the interfacial area. Once you know the interfacial area, then you will be able to calculate what should be the volumetric mass transfer coefficient, because there will be a mass transfer from the gaseous phase to the liquid phase through the interface, and overall concentration differences will be the what is that driving force, and based on which there will be a that is how much moles or mass will be transferred due to this concentration gradient. that will be proportional to this concentration differences. So, based on which you can get the proportionality constant at the volumetric mass transfer coefficient. This volumetric mass transfer coefficient actually is a product of the individual mass transfer coefficient and what is that specific interfacial area. So, in that case, this specific interfacial area to be actually estimated by this method or other method like a chemical method you can calculate. So, generally photographic method, by photography you can have this specific interfacial area as 6 f alpha g by d32. For that you have to calculate the outer mean bubble diameter. To calculate that outer mean bubble diameter, you have to use camera taking a snapshot of that bubble and then analyze by what is that software, image software or some other suitable software you can use, and after analyzing that individual bubble size, then you have to calculate this outer mean bubble diameter. So, in this way you can get interfacial. Now, one important point you have to remember here, since the bubbles, all the bubble size are not in a spherical in shape, we are just considering the equivalent volume of the sphere, and then we are calculating equivalent bubble diameter. But in other way also you can calculate the equivalent diameter of individual bubbles. Suppose if you are getting the ellipsoidal shape of bubbles, then what you have to do, you just mark it out what should be the here suppose ellipsoidal bubble. Here just measure this major axis and measure the minor axis. If you know that major axis and if you know the minor axis of that, then you will be able to calculate equivalent diameter as L max square into L mean to the power 1 by 3. Here this will be major axis is L max and minor axis will be L mean. So, if you know this L max and L mean, then you will be able to calculate what will be the equivalent diameter. So, in this way we are getting the bubble size and its distribution. Now, once you know this distribution, you can feed this distribution and you can analyze by different model of size distribution. Generally, log normal distribution is one important model by which you can analyze this type of bubble size distribution or droplet size distribution. So, I am not going to details on that log normal distribution here. Up to this it is fine, you have to know this is the way to find out the bubble size. And what is that? Let us consider what should be the rise velocity or terminal rise velocity of the individual bubbles. Whenever bubbles are actually allowed to float in the continuous liquid medium or in a liquid medium, gas liquid medium, what will happen? You will see the bubbles will try to go up due to their buoyancy effect. Now, due to the buoyancy effect, it will be moving up with a certain velocity. This velocity is called terminal velocity of the individual bubble or particle. Now, how to actually estimate this terminal rise velocity of a bubble or droplet? Now, if you consider these bubbles here as shown in your here in the video, you will see from the bottom part of the column, bubbles suppose individual bubbles which is allowed from a syringe or nozzle, that individual bubbles is coming and producing, it is going up due to their buoyancy effect. Now, if you consider this bubbles movement and recording it with a high speed camera, and then you can measure what will be the length or distance that is travelled by this individual bubbles there. Now, suppose this bubbles is here, see this one bubble is moving up due to the buoyancy, due to his buoyancy effect, and it follows a certain path. And if we measure this length, with respect to time, then within a certain period of time like delta t, if we are considering that this to this length is travelled, and then we can say that what will be the rise velocity of these bubbles. So, this rise velocity will be equal to delta L by delta t. So, here if suppose this bubbles is go straight, then only simple this to this length will be there. So, that will be your rise velocity. So, delta L, that is distance that is travelled by the bubble per unit time delta t. So, this will be your terminal rise velocity. Now, this rise velocity may be sometimes faster, may be slower. It depends on the size of the bubble. If suppose bubble size is larger, then you will see that it will move fast. It will be moving at high speed and high buoyancy effect will be there, and because of which it will be moving higher. So, in that case, the residence time of the bubbles will be, that means how long it will reside in the column in the liquid medium, that is called residence time of the bubble. The residence time of the bubbles will be here in this case lower, because higher buoyancy effect due to the larger size bubbles. But if you produce the smaller bubbles, what will happen, that their buoyancy effect will be low, and because of which its terminal velocity will be very lower or low. So, in this case you can expect that the bubbles will reside longer time in the column. So, in that case retention time or residence time of the bubbles will be more than earlier. So, here retention time, or you can say that residence time of the bubbles, that depends on the size of the bubbles. So, that is why sometimes some processes it is one of the important factor where you have to consider the residence time. Suppose in the same example, carbon dioxide gas absorption in the liquid. Now, you have to allow the bubbles, carbon dioxide gas bubbles for longer time in the column, so that your mass transfer will be more. If size is higher, if the bubble size is higher, what will happen, immediately it will go up and it will be collapsed at the surface. So, in that case you may not get the 100% transfer of the carbon dioxide gas to the liquid medium. So, in that case you need more residence time. Even some specific reactions, also gas liquid reactions, sometimes it needs more residence time for slow reaction. So, in that case you have to produce more finer bubbles, so that the residence time will be more. So, this is one important factor. So, all this residence time, in bubble rise velocity, all depends on the medium properties, or you can say that physical properties of the system, like surface tension, like density, like viscosity, all those things. So, here one important correlations by which you can calculate what should be the rise velocity of the bubbles. Once you know the surface tension of the system, once you know the size of the bubble, once you know the density difference of gas and liquid, and then you will be able to calculate what should be the bubble rise velocity. Once you know the bubble rise velocity, then what should be the residence time of the bubbles in the column, provided that you have to have the length of the column or length of the liquid medium in the column. So, in this way you can calculate what should be the bubble rise velocity and residence time of the bubble. Similarly, for droplet also it will be the same way to calculate this residence time and the terminal velocity of the droplet. And another one important correlations I have to say here for equivalent bubble diameter. If suppose a bubble is produced and it will be distributed through a distributor, and the distributor hole size is d0, that is orifice diameter, it is called orifice. Through the orifice the gas is coming out from the distributor, and then in this case the orifice diameter, if it is d0, once you know that orifice diameter and the physical properties of the system, then you will be able to calculate what should be the equivalent bubble diameter that is coming out from the distributor. So, this is the formula that you can directly use to calculate the equivalent diameter. So, this equivalent diameter, if you substitute this equivalent diameter here in this equation, and surface tension and density of the systems, then you will be able to calculate easily what should be the bubble rise velocity and also the residence time distribution. And bubble coalescence, one important aspect in this case, because you have to know how actually this coalescence of the bubbles happened. Here you will see there are several methods are actually explained by different investigators, that when two bubbles are coming to each other and how they are actually colliding to each other, and they are joining to each other and making a bigger bubble. Suppose two small bubbles are coming to each other and they collide first, and they will trap a small amount of liquid between them. After that, what will happen, that when they will trapping between them, the small liquid film will be there, and that liquid film drains until the liquid film separating the bubbles and reaches a critical thickness, and the film then ruptured and bubbles join together, and then bubble coalescence will happen. The coalescence of the bubbles, that means the two bubbles will come, or two or more than two bubbles also may come to each other at a particular conditions and getting joining to each other and making a what is that, bigger bubbles. So, this is called coalescence. And breakup is what? Due to the inertia effect, that is turbulency of the flow, you will see two bubbles will come to each other and colliding to each other, sometimes gaining some inertial effect, and it will break up into a two bubbles. So, this is called breakup efficiency. So, there is a coalescence and the breakup. So, in a particular process, when you are doing that process based on this, what is that, interfacial production by gas liquid operation or liquid liquid operation, simultaneously coalescence and bubble breakup will happen in the system. So, that what would be the rate of coalescence, what would be the rate of breakup, that you have to know for further analysis of the process and modeling of the system. So, here we are not going to details of that rate of that bubbles and breakup, and this is not the scope of this courses. So, this will be discussed in further other courses in the MOOCs. I think in multi-phase flow systems it is I think given in details there. So, you can follow. Now, another important aspects that if you are producing these bubbles, what would the maximum stable size of the bubbles can form, that depends on the what is that, viscosity of the liquids, and what is that forces that acting on the surface of the bubbles, and there will be a suppose flow rate of the liquid or gas in a system, then what would the liquid velocity fluctuations acting over the distance of order of that bubble diameter, that is main important factor to actually break up of the bubbles and also coalescence of the bubbles. So, if you know that velocity fluctuation, that is generally represented by this average of this square of this velocity fluctuations, it is generally depends on the energy dissipation per unit volume in the systems and also size of the bubbles. And the doctoring force for the resisting of this deformation due to this velocity fluctuation imposing on the surface of the liquid, and that will be balanced by that what is that surface tension acting that at the gas liquid interfaces. So, surface tension is very important there, that surface tension will actually resist the deformation of the bubbles. Now, at a certain condition, you will see these two forces will be in such a way that at a particular stable condition of the bubbles, surface tension forces will balance the other forces, so that the bubbles will get the stable conditions. So, in that case, it will be calculated based on this equation. This will be at the critical condition, that critical condition will be represented by the critical Weber number, and this critical Weber number, this is nothing but WEC, that will be equal to what is that, rho L U square dB bubble diameter at that critical bubble diameter. This is this is dB rho U square dB by sigma. So, this is your critical Weber number. So, this critical Weyburn number, it will be generally 1.18 for this stable bubble size, and in this case what should be the energy dissipation? This energy dissipation rate per unit volume will be EV, that means how much energy is supplied there. You have to calculate the kinetic energy and then you have to divide it by total volume of the gas liquid mixture, then you will get the energy dissipation rate per unit volume. And then sigma is the surface tension, rho is the density of the liquid. So, once you know this surface tension, density and average energy dissipation rate and the critical number is 1.18, then you can get the maximum stable bubble size there. Now, interfacial area, once you know this bubble size, then what should be the specific interfacial area? The specific interfacial area is defined as surface area of the bubble divided by volume of dispersed bubble bed in the column. So, that will be SB is the surface area of the bubble and this will be VB by epsilon g, this is your volume of dispersed bubble bed, and finally, you can get this 6 epsilon g by dB D32. We have already told earlier that I have given that this specific interfacial area will be this. So, through this interfacial area you can expect the mass transfer there. And what will be the number of bubbles that you can calculate based on this? Once you know this interfacial area and gas hold up, then you can get this what is that number of bubbles, and this here one terms is psi is defined as 1 by 36 pi into dB32 by dBe equivalent to the meter cube. That depends on the shape of the bubbles, and for spherical bubble psi should be equal to 1 by 36 pi. So, in this way you can calculate what is the interfacial area and the number of bubbles. Another important aspects of the multi-phase flow system is mixing of the phases, because mixing will give you the system whether it is homogeneous or heterogeneous systems. Sometimes homogeneous system means here the concentration of the gaseous particles will be distributed throughout the column uniformly. So, that will be your homogeneousness, and heterogeneous, it may not be distributed in all sections of the column equally. So, in that is heterogeneous. So, it depends on this homogeneousness or heterogeneousness depends on the degree of mixing, how these gas and liquids are mixing in the column. So, you have to know what should be the degree of mixing in the particular operations, and based on that mixing what should be the performance of the particular processes, then you can calculate there. Generally you will see that if you are getting more mixing, sometimes some physical processes will give you the better performance. If you are getting sometimes the heterogeneous mixing, some specific process you may get the more advantage or more performance of that system. Now, if you are having the physical absorption, in that case homogeneousness, that means more mixing, sometimes it will give you the what is that favor of that process, and sometimes heterogeneousness also, sometimes it will give some heat transfer operations, it may give the more advantageous or more preferable for the particular processes. But some processes like adsorption processes like gas and solid mixing, in that case back mixing if it is happened, so higher mixing may not give the fruitful results for that. Maybe their reduction of that proficiency or efficiency of the particular process will be there. So, you have to then optimize in which condition of this mixing or what degree of mixing should be suitable for that particular processes. So, in that way you have to know the mixing processes, and to calculate the degree of mixing, generally you will see two parameters are being estimated. One is residence time of the that is interfaces like bubbles, droplets or particles through which the mass transfer will happen, and what is that other important parameter, like it is called dispersion number. Dispersion number is basically one parameter which is being used to calculate the degree of mixing. If dispersion number is more higher, then more degree of dispersion will be there. if dispersion number is lower, it does means that there will be less mixing there. So, how to estimate that mixing characteristics? Generally, tracer techniques are being used to calculate that mixing characteristics, and in that case one tracer particles are being inserted into the column, and then finally the sample is being analyzed with respect to time, and then you will get a certain profile of that, and after analyzing that profile you can estimate the dispersion number there. So, I am not going to deep on that particular estimation of this mixing processes here in this course, and it will take I think another 2-3 lecture to discuss this mixing. And this is also not the scope of this process here, this lecture also, and so you can get it from other courses, that mixing characteristics of the multi-phase flow systems. So, here I want to stop. I would suggest to go further reading if you are interested to analyze the process based on the mixing and model the process, then you have to go further reading for that. What is that? The books that you have to follow for further understanding of this mixing process, even multi-phase flow systems and bubble size analysis, all those things. So, thank you for this.